to go. Okay, good morning, everybody. So today we are going to make a next step into the machine learning for automated experiment and talk a little bit about how does it work if it is implemented in real time. So obviously in the form of recording. And also talk a little bit why we need to make it explainable and how to enable the human in the loop intervention in the automated experiment. So if you never heard about these words before in the context of automated experiment, that is natural. So this field is emerging right now. And there are reasons why many of these concepts are easier to develop first in the context of microscopy rather than materials design, or let's say theory. Second thing is that if this title sounds like the collection of the buzzwords from the last year or two, this is also actually natural because the concepts of how to bring human in the loop appear in multiple applications of ML. So not only experiment, also things like labeling and so on and so forth. So anyway, let's start with the brief recap. So we looked at the Gaussian processes. We looked at the everything related to kernel and kernel parameters. We looked at how you add structural elements and structural mean function and Bayesian inference. We talked about the Bayesian optimization and acquisition function. So by now, these are the concepts that you heard about many times. And also, these are the concepts that you potentially explored with the collabs. So again, the reason why the collabs are super useful is because after you use them for some time, they become a part of your intuition, and you can use them as the part of the decision-making concept and the experiment planning. If not, translation from the domain-specific language and ideas into the language that can be used for the design of machine learning models can be complicated. So nonetheless, for Gaussian processes, we looked at the examples of how it works. So we assume we have some ground truth function. We don't have access to it, but we want to discover it. We've done some measurements. Based on these measurements, we can reconstruct the function and its uncertainty. So if we do it basically purely on data, this is called surrogate model. So Gaussian process itself is purely data-driven. Bayesian inference is the case when we have a model and have some idea of the parameters. Structured Gaussian process is when the mean function is basically represents a partially known physics of the process. So one very important thing is that all the examples that we've seen so far, either in Colab or in lectures, were plotted as the one-dimensional function, as a function of the one-dimensional argument. So the reason why it is done is entirely obvious, because it's difficult to represent high dimensional functions. But the first very important thing is that, strictly speaking, our X does not have to be R1 space. It can be much more complex space. It can be, first of all, it can be multidimensional spaces. So in this case, we talk about the parameter optimization. It can be a non-differentiable space. For example, problems of the molecular discovery can be represented as the exploration of the chemical space of the molecules. And it can be even something else, for example, the space of the local images. If you want to learn structure-property relationship, this can be an image. With respect to Y, situation is a little bit different. So if we have the Y function to be multidimensional, then we need to be very careful about how we formulate our Bayesian optimization problem. So we either make it multi-objective or we make it a discovery. So it sort of depends what you want to accomplish. So we also talked about the acquisition functions and policies. So the principle of the Bayesian optimization is that based of the data, we create a surrogate model, and and its uncertainty, and then having the surrogate model and its uncertainty, we can choose where to perform the next measurement. However, in order to do that, we need to have some way to balance the prediction and uncertainty. So on the one extreme, we can have purely exploratory policies. So think about it as a fundamental science. What we want to do is to minimize the uncertainty of our function. And we really don't care what value these functions will take. We just want to understand it as better as possible. On the other hand, there would be purely greedy exploitation policies where we think where the maximum is and we try to get there as quickly as possible. The problem with the greedy exploitation is that very often you find the not a true maximum, so you can easily get trapped into the local metastable optimum. So that's the limitation. And practically, if you want to optimize but also keep your mind open, you start to balance the exploration and exploitation. So this is done in the form of the acquisition functions, and in the context of the Bayesian optimization, acquisition function is the equivalent of policy in the reinforcement learning. So the difference between the acquisition function and Bayesian optimization and reinforcement learning is that in Bayesian optimization, we typically plan one step ahead. In reinforcement learning, we really need to explore how the sequence of several steps would be different from making the steps one at a time. So that is the reason why the Bayesian optimization is usually called the myopic optimization workflows. And then our full cycle that we have is kind of what is done in the Freitas review. You start with the measurements, you reconstruct the function and uncertainty, you combine them in the acquisition function, which balances exploration and exploitation. You find the maximum of the acquisition function, you perform the measurement at this location, then you recalculate your function, you recalculate your uncertainty, you recalculate the acquisition function, and then you repeat the process over and over again. So notice, and this is kind of the hooks for the subsequent discussions, notice that we know that the way we choose the policies should depend on our experimental budget. So if we have very few experimental iterations, it makes sense to go for the fully greedy policies. So if I can run only one or two experiments, I need to make my best guess about where I can get the result, do the measurements there, I'm good to go, I don't have any budget to explore. So at the same time, if I know that I have the fairly large experimental budget, it sort of makes sense to first put my time and effort into the exploration and only then start to switch towards the exploitation. Another interesting thing is that I'm sure that people are doing it somewhere, but at least in the books and the review papers that I've seen, the possibility of tuning the acquisition function during the experiment is not explicitly brought up, even though it seems to be intuitively obvious that the acquisition function does not have to remain the same during the experiment. So as I said, you can start with the exploration and then make it much more greedy throughout the experiment. So that's another kind of thing to keep in mind. Now, how would the Bayesian optimization actually work for experiment? So we started to work on it primarily. First, Maxim was developing the bio libraries for STM. That was roughly 2019. So then COVID happened. Then as a result, most of our developments have been done for the first 6 months purely on the theoretical models. So I still have quite a few papers on the use of the Bayesian optimization to explore Ising model. So very convenient because no lab, but you can spend 12 hours a day programming. So, but then COVID restrictions become easier, and Rama got back to the CNMS and they implemented this early version of the Bayesian optimization on one of the Cypher microscopes. So let's not go in the technical details because at that time it was exceptionally difficult. So the algorithms were quite ineffective. The connecting the control computer with the instrument is not trivial. So now the situation is changing, but as I said, at that time, if you want to be the first, you really need to go extra 5 miles in enabling the engineering controls. But anyway, the first experiment that we set up was the piezo response force microscopy when we try to measure the hysteresis loop. So the workflow was that you have a sample, you measure the response signal, you extract the hysteresis loop. So this is some measurable parameter. We take the hysteresis loop and determine the loop area. We use this loop area as the optimization function. And then we basically tell the Gaussian process that we want to explore our sample plane to discover the regions where the hysteresis loop area is maximum. So this is a classical optimization. In this case, we treat the sample as literally as a black box. We assume that we don't know anything about the sample. And then we perform certain form of fairly expensive measurements point by point. And we try to see whether the strategy would be superior compared to the grid-based measurements. So it's a kind of really credit to Rama's persistence that it worked. But the results, to be honest, were very disappointing. So this is the ground truth. So in some cases, we can actually measure the signal on the grid. This is what the Gaussian process have discovered. And if you compare the ground truth data with the Gaussian process prediction, it actually worked, kind of, sort of. You found the regions which are plausible maxima. But generally, if this is the result, so you spend a tremendous amount of time and money into implementing the Gaussian process on the real world instrument, and this is what you get in the result, that's really not worth it. So why is it the case? This is the case for two reasons. From the point of view of the Gaussian process, very often we deal with the ground truth functions which are very ill-behaved. So for example, here you can see that we essentially have some form of ferroelectric domains. So some of them are big, some of them are small. In fact, some of them are almost 1 pixel wide. And you have already seen as an example of our previous lecture for the Gaussian processes in the latent space of our encoder, is that this type of function cannot be represented by GP kernel very well. So to put it simply, if the features are very small, then the kernel widths have also to be very small. But if the kernel length scale is small, then the Gaussian processing does not give us any significant advantage compared to the normal measurement. In fact, we have to start with discovering this kernel, and that takes us time. So practically, after spending quite a lot of time experimenting with the Gaussian processes workflows, both for electron microscopy data, sort of STEM, structural, EELS, and SPM data, it seems that in general case, Gaussian process can give us advantage of 2 and 3 in terms of the number of the scanning points. So that at least theoretically can make experiment twice or thrice faster. But the price for that is that our scanning trajectory becomes totally weird. So we need to go in the, instead of having the rectangular scan for which the microscopes are optimized, we have to do measurements in sort of strange sequences. And then we start to have with the things like drift, the fact that if you go from here to here and then back, you're not going to come back to the same point. So you need to compensate it somehow. You have to deal with the fact that this type of motion also takes time. And basically, if you put all these considerations together, you come to conclusion that simple GP for microscopy for imaging part does not make sense. It is useful for tuning the microscope, but not for anything else. So what shall we do? So the good thing is that by the time we implemented the experiments, we already realized that this problem can arise, and therefore we were already thinking about the solutions. And going back to this the Freitas picture, remember that, as I mentioned, that this axis, our argument, does not have to be a scalar. It can be something more complicated. And complicated can be anything you can possibly think about. For example, it can be molecular structure. So in this case, as I said, it is the chemical space exploration. Or it can be the image patches. And then we started to realize that maybe we are thinking about the everything related to the application of the Bayesian optimization and Gaussian processes in experiment in the wrong way. Because practically, when you run the microscope, you basically never deal with the black box exploration problem. So when you run the microscope, you always take an overview scan, and then you select the locations for the specific measurements. And this is the thing which is common across a very broad swath of the microscopic community. So we do this in scanning probe microscopy of all kinds. So we take the topographic image, and then we choose the locations for the IV measurements, for PFM hysteresis loops. We take the atomically resolved STM images, and we choose locations for the CITS. We use the same thing for electron microscopy. So we do the overview scan, somehow identify objects of interest, and then we choose the locations for EELS measurements or 4D STEM or what's not. So very often, of course, we decide to automate the process and do the measurements on the grid. But first of all, we do select the locations where to deploy the grid measurements. And secondly, we intuitively know that grid is not the best strategy because of the beam damage and the fact that most part of the image are not interesting. So we use exactly the same thing for other techniques. For example, if you are doing nano-indentation, it is the same principle. So currently, when we look at we choose the locations for the nano-indentation, we have access to the optical or SEM data. So it can be just optical image, it can be some form of fiduciary marks that allow us to compare the SEM image, BSD, and choose the locations for the nano-indentation measurements accordingly. So we never deal with the black box experimental setups, which basically means that if we take this consideration and turn it on its machine learning side, it means that we actually need to explore the high dimensional spaces. And the high dimensional spaces in this case is going to be sampled by the represented by the local microstructure. So that's a kind of an important thing. That was one of the kind of turn point at which we started to realize what type of GPU we need. And then, of course, the same thing applies for problems like molecular discovery, because there you need to operate in the high dimensional spaces of the molecules. So we know that classical GPU is limited to low dimensional spaces, and the fact that the correlations are defined by the kernel function. We don't use the knowledge of physics. We don't use the cheap information available to experiment. So what we can do is this cheap information is available. We can use this high dimensional proxies to navigate our experimental space. But then the question becomes, if our proxies are high dimensional, how do we deal with the fact that GP works well only in low D spaces? And this is exactly where the deep kernel learning comes into play. So what is deep kernel learning and how does it work? So, I mean, this is obviously can be the whole set of lectures by itself. As I mentioned, for the purpose of this school is to come up with the minimum list of concepts that are required to actually start doing it, and provide the code and notebooks that allow you to actually play with the data and apply it to own problems. But let's look at it a little bit. So we are not going to go deep into the detail, but let's look at the big picture, and then let's look at the application. So the big picture here is that the deep kernel learning is basically the combination of two neural network architectures that we already talked about. One is variational autoencoder. That's why we actually talked about the variational autoencoders. And the second is the Gaussian process. So the way they work is that you start with some input object, which can be very high dimensional. It goes through this convolutional funnel. I mean, it can be DCNN, it can be a multi-layer perceptron, it can be graph network. It is entirely up to you. So the details really don't matter that much. They're determined by the dimensionality of the input object and sort of effectively the principles accepted in the community. So this part of the deep kernel learning takes your high dimensional object and compresses it to the small number of latent variables. So very often we choose two latent variables. Sometimes we can choose large amount, but depends on the complexity of the problem. Then this defines the latent space. On top of this latent space, we have the Gaussian process that builds the relationship between the latent variable and our target functionality. So there are several subtleties here. So the target functionality can be a scalar. So in this case, we have a Gaussian process that operates on low dimensional space and reconstructs the scalar function. However, it does not have to be a scalar. So Maxim built the code implementations that allow the target to be a vector, for example, the whole spectrum. And in this case, you basically have the multiple Gaussian processes that basically create it point by point. So this is great. Now, how does it work? So first of all, question is, how is it different from the Gaussian process running on the latent space of the autoencoder? The answer is very simple, that if you create your problem by starting with all the data, using the variational autoencoder to create the Latin embeddings and run the Bayesian optimization over this latent space, in this case, the embedding vector is static. It does not change. And that can be good for the problem, but in many cases, it would be suboptimal for the problem because that's what was our example with the cards and the Ferrocim model in the previous lecture. So if the structure of the latent space is determined only by correlations in data, there is absolutely no guarantee that this structure is optimal for the discovery process. In the deep kernel learning, this whole architecture is actually trained jointly. And by virtue of trained jointly, it means that the embeddings are changed at each step of the training process. So they're dynamic embeddings. And as you've seen with the example for the cards, it makes them much more flexible and much more suited for specific tasks that we consider. Obviously, at the cost of other possible tasks. So for the VIE, the embeddings are kind of equally bad for all applications. In GP, they are in the DKL, they are very good for the target application and much worse for the non-target applications. Now, let's see how this process applies practically. So what is the workflow in this case? So the way it works is that we start with the structural image. So again, doesn't matter what method you use, doesn't matter how many layers are in this image. So it can be a scalar signal, it can be multi-channel signal, then we just kind of create our objects which are multi-channel. It can be pretty much anything. So once we start the image, we assume that there is some relationship between the local domain structure and hysteresis loop, or specifically some parameter of the hysteresis loop. So for example, we can build the relationship between the local domain structure and the area under the hysteresis loop. So this is what we want to discover. So the way we proceed in the normal experiments, so if human runs the microscope, is that we take the measurements everywhere, we measure the hysteresis loop everywhere, we create a map of the hysteresis loop area, we build the correlation between the local domain structures and this local hysteresis loop area. So that's what we have been doing for quite a while. In the DKL experiment, we proceed differently. We take all the structural data, so that's rapid operation, and we split it into the collection of the patches. So patches determine the local microstructure. We obviously create multiple patches out of the image, so this is just an image representation. And again, and that's a fairly standard approach. We kind of do that when we do any kind of the sliding window transform analysis of the images. If we use the deep convolutional network for image segmentation, again, we do exactly the same thing because the first layer or layers of the convolutional network is essentially a patch representation, but it's called filters. So the approach is very universal. And from the physical viewpoint, it kind of implicitly suggests that there is a correlation between the local structure and the functionality of interest, and this correlation is strong. At the same time, we implicitly assume that there is, let's say, no correlation between the hysteresis loop area here and the domain structures over here. Going forward, and if you have a question whether we can test this assertion or not, we kind of sort of can test it by feature engineering and discovering the predictability. So we can test hypotheses. We don't so far have the ML method that allows to do it in that automated fashion. But again, nobody has finding the optimal features that can represent certain phenomena. This is the same type of problem as the discovering the Kolmogorov complexity for algorithmic development. So if something has simple solution, it doesn't mean that you necessarily can find it. And if there is none, if you are not sure, then you can only test the hypothesis and see if it works. So anyway, going back, we have the collection of the image patches. So then what we do is we take one arbitrary location in the image, measure our hysteresis loop, and calculate the, let's say, the hysteresis loop area. And then this is where the real trick with the deep kernel learning comes into play. We train the network having access to all features, so we have all the patches, and having access to only one target. So in this case, this looks like a very weird thing to do. So we are used to the fact that when we use the neural networks, we either have the equal amount of features and target, and then we build the relationship between the features and targets, or we have features but we don't have targets, and then we have the unsupervised learning. So in this case, we have all the features and only one target. This is one of the places. So remember that I've mentioned many times during this workshop that part of the reason why the hands-on programming experience is absolutely required to apply machine learning to physics problems is because there are certain concepts that emerge in the context of machine learning that don't have equivalence in the way that we learn physics normally. And what I mean by that is, at least for me, and I suspect for all of you, the concept of the semi-supervised regression would be meaningless, right? So imagine that you want to determine some function and you have the XY pairs. So we learn the relationship between them to its supervised learning. But let's assume that we have many more X values than Y values. If we operate in the low dimensional spaces, like one-dimensional, two-dimensional, three-dimensional, that's really doesn't make any sense. If we have multiple Y values and only few X values, the only points that make sense are the only points that are useful are those for which we have XY pairs. All other X's don't tell us much. And in low dimensional spaces, it's true. But in the high dimensional problems, this is no longer true. Knowing what the X can be, having X at multiple locations, defines the manifold on which our data sits. And if we define the manifold, we can build the relationship between X and Y much better. So if we do it in the static learning regime, this is called the semi-supervised regression or semi-supervised VIE. For our purpose is the reconstruction. If we do it in the active learning setting, that's what the deep kernel learning is actually accomplishing. So we can train the network having all the features, meaning all the patches, and only one value of the target, and this network will make sense. Now that you can ask a question, what are we going to get? So imagine that this is the feature which corresponds to this target. So in this case, if we take a different feature, so from different part of the image, and use it for prediction, we are going to get same target. I mean, the network is just trained on the one example. So what's the purpose? And the purpose is that, yes, the target would be the same, but the uncertainty would be much larger. So if we use this as our original example, so this is our feature for which we know the target, then this target would be predicted with a very low uncertainty. But for the feature that looks very different, the prediction will come with a much higher uncertainty, which basically, once we put the uncertainty into play, instantly tells us how we close the loop the same way as we did with the Bayesian optimization. We choose the next location for our measurement where the corresponding feature comes with the highest predictive uncertainty. And then we do the second measurement. So now we still have all the image patches. Now we have two measured points. We retrain the network, and then we repeat the process ad infinitum using the same type of approaches as Bayesian optimization. So to represent it a little bit, differently, we start with the structural data. We measure a spectrum. We define what physics we're interested in. So in our case, it is hysteresis loop area. We train our DKL model. It gives us the prediction. And then based on the prediction and uncertainty, using the same policy principle, we decide the next point. And then we continue this process. So there are two kind of new words which one of the difficulties working in this area is that it is necessary to develop your own vocabulary, because first of all, we need to somehow define the process in such a way that it maps onto how the microscopy community works in general. And secondly, since vast majority of the work in the field of Bayesian optimization, stochastic planning, and reinforcement learning are done in the purely computer-based concepts, they simply don't have words that can be used for the description of the experimental workflows. So practically now we have two key notions. One is the scalarizer. So scalarizer is the function that transforms the spectrum into the measure of interest. So it can be anything. It can be integration over the interval. It can be parameters of the peak fitting procedure. It can be the ratio of the peaks. It can be pretty much anything that you can come up with. The only thing that matters is that if you look at the spectrum or you do some analysis of the spectrum, you need to be able to say that this is how I convert it into the function of interest. So obviously scalarizer comes with the value, and in the prediction it also comes with uncertainty, but that's the primary definition. So a second notion that we define is the experimental trace. So experimental trace is the collection of image patches and associated spectra acquired during the experiment. So basically it means that first I did measurement on this location and I measured this spectrum. Then I've done measurement on this location and got different spectrum. So basically it traces the collection of the patches and spectra. Practically, if we run the experiment on the microscope, we have the global image and the trace. If we work on the pre-acquired data when we set up and tune the workflow, we can repeat the experiment many times. But that's kind of important definition. One important thing here is that we collect spectra, but not only scalarizers. So again, this concept can be extended for other exploratory problems. For example, this can be pick the molecular structure out of the structure collection, and rather than measure a spectrum, it can be use the DFT to calculate the properties that you're interested in. So define the scalarizer can be either you already calculate the property or DFT gives you some prediction. For example, prediction can be electronic structure, and then you use your scalarizer can be homoluma band or the redox potential or what's not. Then you train the DKL model, which would be trained in this space using this as the target functionality, and then the cycle repeats. Exactly the same thing can be done for the materials discovery, except that in this case, you start with the collection of the structural data sets and kind of continue over and over. Big limitation here is that for the time being, we don't have the generative component. So remember that VIE is a generative model. You can sample from the latent space where there is no point belonging to the latent distribution. And that's why it's generative. So DKL is different. DKL is effective, but the present versions are not generative, meaning that you need to provide it with the list of original guesses. The fact that it can be incorporated in the more complex workflows when there is some form of the generative process, that's a different story. Now, would it work for other experimental setups? And the answer is, of course. So now we switch to the work that has been done by Kevin Roccapriori. So important thing is the engineering control. So for SPM, as I mentioned, everything has to be essentially hacked. Therefore, there is the ratio of the visible result and the work done behind the scene is about the same as on the iceberg. The great thing about the electron microscopy is the fact that many manufacturers now provide the APIs that allow you to deploy the code directly on the instrument. So for neons, the big breakthrough was about 2 years ago when the Neon came up with the new iteration of the Swift software, which basically accelerated the deployment of the ML codes on the microscope by orders of magnitude. It used to be the fact that you need to have 3-4 people in the room to hack into the system and run the microscope and make sure that your human custom-based controller talks to the microscope. So that at that time, the progress was really very slow. With the APIs, it is much faster. And the interesting thing is that by now, scanning probe microscopy community is still kind of wobbly about it. There are APIs for Bruker or NanoSurf. There is some development program at Oxford, but electron microscopy seems to be much more aggressive about it. So, for example, we're now having a development agreement at UT with the Thermo Fisher because they have the environment that allows to deploy the codes on the Thermo Fisher instruments. And Joel has the similar agreement with the PNNL along the same lines. So it's really starting to progress really fast. However, 2 years ago, the only game in town was the Neon. And this is the example of that automated experiment done by Kevin using exactly the same DKL approach. So in this case, the scalarizer was very interesting. So this is the object. This is a flake of the two-dimensional material. This is the yield spectrum. So the yield spectrum instantly shows you that this is the zero loss peak. This is one peak. This is second peak. And since you're in the plasmon energy region, This peak corresponds to the bulk plasmon. This peak corresponds to the surface plasmon, or presumably correspond to surface of bulk plasmon. So what we can do is define the workflow where we start with the yield spectrum, cut off the zero loss part, fit the remaining part of the spectrum with the two peaks with kind of approximately known positions, and then we take the ratio of these two peaks and we use it as a scalarizer. So notice the elegance at which we combine the physical intuition and physical driving and machine learning here. Machine learning doesn't know physics at all, so it's a purely correlative discovery. However, humans have idea about what type of physics you are interested in. In this case of this particular material, we are interested in the emergence of the surface plasmons. So with this in hand, we define our scalarizer as the ratio of the surface plasmon intensity to the bulk plasmon intensity. And with this, we create a scalarizer that we then provide to the ML algorithm and tell it, do your best. This is how it works. So again, this movie is 2 years old, but it's still amazing because it basically shows you how the microscope in real time explores the flake, and the red locations is where the microscope chooses to take the measurement. So this is the stem image. This is the acquisition function image. So you can see how the microscope explores the new regions and how it kind of attributes attention to specific regions on the sample. So if you do this type of experiment on several different flakes, however, you start to notice something interesting. So, and the thing that you notice is that the experiment definitely worked. So in this case, the microscopes have been exploring a little bit these regions, and then it focused on this part of the flake. Here it explored this region. Here, however, for whatever reason, it really didn't like this edge. Here it sort of explored uniformly this region. It did not explore this region as it shouldn't. So there are no, we don't expect surface plasmons here. It didn't explore this region. But for yet another flake, somehow the microscope that decided that these regions are good and these regions are so-so. So obviously when this worked 2 years ago and we experimented with it for about a year after that, we were ecstatic. So this is the true example of the automated experiment. It works, we learn new things. But then you start to kind of be a little bit critical about it, and you start to notice that you don't really understand of why the experiment progressed exactly this sequence. So, I mean, naive way to think about this data is saying, okay, the physics that we're interested in is maximized in this region. So this is great. We have discovered something. So there are two problems. First of all, we don't know what is special about these images. And secondly, we have no certainty that this is not some form of the problem with the algorithm, or maybe even not a problem. The algorithm, after all, actually has some amount of hyperparameters. And what we did is we tuned these hyperparameters using the pre-acquired data. We deployed the algorithm on the microscope. It worked, but it worked with one set of hyperparameters. Notice that when we do things on the working microscope, we almost never can repeat the experiment for the different value of the hyperparameters, because this is not a machine learning. This is a real world system. So our experimental budgets are limited, our sample drifts, our beam damage accumulates. So repeating things ab infinitum and tuning the hyperparameters on the fly, in the end of the experiment, like it is done in the ML community, is not the right strategy for the automated experiment. So this is kind of another important consideration. Nonetheless, at that time, we were not thinking about it. But what we did was to experiment with other with other scalarizers. For example, we can use the peak intensity, and then the algorithm start to explore the inner part of the flake as it should. So Yongtao have implemented the same type of algorithm on the AFM. So again, this is a tour de force experiment because connecting the collab to the lab view environment working on the different computer is not trivial. So it's really much better if there is a API that allows us to do that. But again, the experiment worked rather spectacularly, and this is the last year paper in Nature Machine Intelligence, where we define the scalarizer as the loop area during the on-field hysteresis loop. And you can see that this is the experimental progress. So the color of the dot is basically the timestamp. So microscope start to explore this part of the domain region. Then it explores here. Then it discovers this region. And then it basically stays and points that the on-field hysteresis loop area is maximized on the ferroelectric wall. If we choose our criterion and pick off-field loop area, it shows us that the hysteresis loop area is maximized on the ferroelastic wall. Again, in this case, it makes sense because we can speculate that for the ferroelectric wall, it is kind of more sloshy in the on-field loop. And here there is a reason the polarization can rotate on the one edge of the ferroelastic domain. But you see, the interesting thing is that this is a relatively simple system. This is just a hysteresis loop measurement, something that we've been doing for 25 years or 20 years as it may be, or on the, actually 25 years by now. So on the material with the very well-defined domain structure, we have only two types of topological defects, ferroelectric walls and ferroelastic walls. And in this case, the microscope produced something that we can readily understand and rationalize. It's not to kind of diminish the strengths of the accomplishment because we can explain it, but the algorithm did not know that. But still, it is a fairly narrow case. We can run considerably more complex experiments. So for example, ferroelectric materials are also nonlinear, and nonlinearity means that if we measure the magnitude of the response as the function of the driving voltage, we can, our dependence is not perfect line as it would be for the linear piezoelectric material. It's actually kind of bent upward. So you may ask a question, so why are we focusing primarily on ferroelectrics? The answer is very simple, because all this work was funded by the 3DFEM EFRC. So if the sponsor expectation is to work on ferroelectrics, we work on ferroelectrics. Plus, there are other reasons why it is technically a good idea. So anyway, in this case, the way we build the scalarizer is we take our data in one location, we fit it by the cubic curve, so it's a fairly robust fit, and then we can use the parameters A, B, C, or their ratios as the target functions as the scalarizer function to guide the experiment. Okay, so in this case, the scalarizer is defined, the materials are more or less known. So let's run the experiment on the lead titanate field. So material with the well-defined domain structure. In this case, you can see that our algorithm explores different part of the sample, but then it decides to go in one specific location and kind of stay there, and maybe kind of jump between this location and this location. And then we ask ourselves a question: does it mean that these are the regions where there is some specific behavior maximized, or maybe there is a sort of metastable minimum? Because look at our acquisition function. Our acquisition function actually has a lot of details, which are all roughly comparable, but somehow algorithm decides that some of these locations are better than others. Another example is hafnium oxide. So very interesting material. the first binary ferroelectric. So when the first papers about it were published about 10 years ago, nobody believed that the binary oxide can be ferroelectric, but it is, and now it's probably one of the biggest developing areas in ferroelectricity because these materials are compatible with the silicon backend fabrication. In other words, you can use it for the FRAM, unlike the normal ferroelectrics. But in this case, it's clear that our microscope has explored, the part of the sample, and that it really wants to stick here. And we saw this behavior, again, for other case systems. We saw the same type of behavior for eels. We saw the same behavior for the 4D stem, which basically tells us that we need, rather than simply define our parameters and tune the policies before the experiment, we need to generate the new kind of tools to monitor and direct the automated experiment. So just to summarize it slightly differently. So in conventional microscopy experiment, the human runs everything directly. So conventional microscopy is actually now in the state of the dual technological debt that human does everything, define, scan, positions the probe, define measurement parameters. So tuning operations can help, but ultimately the discovery process is driven by the human. When we have the automated experiment, this is the machine learning agent that we tune before the experiment, and then the machine learning agent basically sends the commands to the instrument. But for any automated experiment, we need to define policies, meaning the rules how the algorithm behaves on different situations. And the reason why we need to define policies is because we cannot envision everything that the microscope can encounter. So microscope is always going to encounter something that it haven't seen before, because otherwise it's not science. So if the microscope is going to encounter something unusual, we cannot come up with the prescriptive behaviors. We define some form of the policies based on previous measurements. But for the time being, our policies are fixed. And sometimes it works. Sometimes it clearly doesn't work. And there are a lot of examples when we are not sure whether it worked or not. Which basically brings us to the 2 points. First of all, how do we explain the progression of the automated experiment after the experiment? So how do we make it explainable? And related to that is how do we control it during the experiment? So in this case, again, we are going to where no one has gone before, neither in the microscopy nor in problems like molecular discoveries and what's not. So the fun thing to do is to see how this logic can be applied for molecular discovery or kind of controlling DFT or whatever. Okay, so let's kind of recap where we are now. We have 3 types of experiment that we classify based on the principles by which we make decisions. So the first type of experiment is the direct. So when we acquire raw data, label the data based on prior knowledge or interest, train convolutional network, use the pre-trained network to analyze the data, and perform the experiments based on the predefined objects of interest. So the example of this workflow can be use the deep convolutional network to find all the domain walls or find all the silicon atoms in the graphene. So in this case, our policies are shift. The technical difficulty here is that we need to have a stable DCNNs that don't care about the out of distribution shifts. But in this case, everything is fixed. So myopic discovery is what we talked about in the concept of the deep kernel learning experiment, is when we acquire data, evaluate it, identify some, check some stopping criteria, which can be experimental budget or safety or what's not, train Bayesian optimization using the parameter we want to optimize, and then we go in circle. So in this case, the decision is made on the every step based on our known optimization target. So multi-stage discovery is pretty much completely unknown in the field of microscopy for the time being. So this is similar, but it is a kind of reinforcement learning type of criteria where the reward becomes available after multiple experimental steps or even in the end of the experiment, and we need to propagate to create the value. So we are not going to go there because that's something that I'm currently working with a group at the Google Brain to build the framework for this type of analysis, but it's a bit too easy, a bit too early to talk about it. We are sort of at the stage when we learn to understand each other. Nonetheless, the question becomes, if we deal with the myopic discovery, which is currently our bread and butter in the automated experiment, how can we bring the human in the loop? And the question, and sort of obviously how we are going to make sense of the observation. And in this case, what helps to do is to look at our experimental workflow one more time and see what are the points of the human, possible points of the human intervention. So we start with the acquisition of the structural data. This is the part that we cannot change because this actually defines, this is a fairly narrow workflow. So it starts from the moment when we have the overview scan. So this is where we start. So however, the first target for the human intervention is the definition of the initial exploration targets. So in the examples I have shown, we take the few measurements, initial seed measurements at the random locations. It actually doesn't have to be that way. We can choose the initial exploration targets based on the prior knowledge or based on the statistics of the initial distribution. So I'll show you the example of how it can be done. But it turns out that the definition of the exploration targets makes a big difference in how rapidly the system can learn. So then we measure a spectrum. So this is a part of the microscope operation. We are not going to change this one for the time being. So we don't have a feedback. We don't have a feedback for the spectrum measurement parameters. Then we have defined scalarizer, which is basically what physics are we interested in here. So in this case, scalarizer does not have to remain constant during the experiment. We can easily start with one scalarizer, for example, the area under one peak, and we can change the scalarizer during the experiment. For example, if we measure the intensity in the certain spectral band, we can simply make this band kind of broader or more narrow or sort of shifted. If we take our spectrum and fit it by some function like 3 fits or nonlinearity, we can easily change the parameter that we look at. So let's say instead of looking at the amplitude of this peak or ratio between these two peaks, we can look at the ratio between those two peaks. Or instead of using the slope or the second coefficient, we can use the ratio of the second and third coefficient in the power law fit. So either select the scalarizer from the list or tune the parameters of the scalarizer if they're continuous. And then once we train the DKL model, we also have some number of the control knobs here. So once we have the Gaussian process operating over the latent space, we have a policy that allows us to balance exploration and exploitation. And again, we can choose the policy from the list. For example, go from the USB to the expected improvement, or we can choose to tune the parameters of the policy. So for example, UCB or E can be made more or less greedy by tuning the, for example, parameter beta in UCB. So this also notice that we can also define the exploration targets. It doesn't have to be initial. So we can give our experiment some time to run, and then we can say, you know what, I can also see this type of objects. Please do some measurements there as well. So this can be not only initial, it also can be the intervention. And the interesting thing is that if we have these interventions, first of all, it looks like that for this specific type of the automated experiment, this is a complete list because there are no other locations where we can intervene. Secondly, these interventions are very different from how the humans are running the experiment. So this one we can understand a little bit, but this one, and especially this one, is not how humans think about the experiments. And then the question becomes, how are we going to monitor the process, right? Because once we run the automated experiment, this is the machine learning agent doing something with the microscope and detecting the signals. So if we want to make the intervention, we need to have some feedback. We need to know what the machine learning agent is doing, and we need to kind of understand what it is doing and how to trace its behavior. So what are our options? So obviously the first and the most direct option is to monitor the exploration of the image space. So the convenient thing about the images is that we are very used to recognize the image, and the experimental sequence is simply the sequence at which the different spatial locations are explored, which basically means that if I have the control knobs, in this case it's an unreal condition, if I had a control knobs during this particular experiment, I would be able to say at this stage, you know what, I think that my algorithm got trapped into these two specific locations. What I really want to do is to tune my scalarizer and see how the exploration changes, or I need to make the agent maybe more curious and less greedy. So turns out that we can come up with some other strategies for analyzing the experiment, and those are primarily tested for the time being, are tested for the offline scenarios, because you really need to test a lot before you deploy. But one of the parameters that we can observe in the offline scenario is that we have access to the model which has been trained on the full experimental data. So what I mean by that, that imagine that you are working on the microscope in real time. In this case, you start your experiment, and obviously you train your model along with the progression of the automated experiment. We take data, we train the model, train model-based predictions. Based on this prediction, we select the next location for the automated experiment. However, when we tune the workflows, we typically do it on the pre-acquired data sets, meaning that we have access to the ground truth in the active learning scenarios. What it means is that we can take our automated experiment and define three types of models. One is the live analysis. So live analysis is equivalent to what you would learn if you are sitting in front of the microscope. So this is the parameters that are available to the model being trained in real time. In the dummy experiment, we also have access to the final decayal analysis. So this would be the state of the model in the end of the experiment. We of course don't have it in the live experiment, but we have it in the post-experiment analysis. And in principle, if we also did the measurement on the grid, we are not going to do it going further in big scenarios, but for testing, we can do that. We can also have the model which is trained on the full data set. And then it becomes very convenient because we can take this complete model and use it as an oracle. So we know that, let's say if you have 100 by 100 pixel measurement, where you measure the hysteresis loop, you have 10,000 hysteresis loops, you have 10,000 image patches. The live model is trained on the small number of patches sequentially. So you start with model trained on one patch, spectrum pair, 2, 3, and so on. So this is the model that learns during the experiment. Final model would be trained on all the data set obtained during the experiment. And let's say if we have 200 experimental steps, the final model would be trained on 200 data points. And the important thing is that the experimental trace on which we train the final model depends on the policies. And in general, it would be different. The complete DKL model would be trained on the 10,000 patch spectrum pairs, so it is available. It is available in full, so no surprises here. So, and then what we can do when we tune the workflows, as I said, we can use the complete model as an oracle, and we can compare the discovery during the different workflows. For example, compare the different acquisition functions like EI, maximum uncertainty, or upper confidence bound, and we can see how they learn. And this is where it becomes super interesting, because if we train the function using the fairly greedy policies, so UCB and EI care about the optimization function, very often we see that initial learning is fast, then the process gets stuck in some location, then it can get unstuck, so it's kind of noisy. If we train it using the more exploratory policies, for example, MU is pure exploration, no exploitation, then the training is actually much smoother. We also can, so I will show you the example of the notebook where it is done, and I kind of strongly encourage you to play with it. In fact, for my group, this is kind of going to be a big part of what we are doing for the next months and potentially years. But for the time being, kind of look at these examples. So there are other things we can do. So if we work with the pre-acquired data, we can also define the counterfactual scalarizers. So in this case, imagine that we run the experiment on the one specific scalarizer, for example, loop area. We can also calculate the counterfactual targets. For example, we can say what would have happened if our next step were loop height rather than loop area. So obviously we can calculate the counterfactual scalarizer only for the next step, because then the progression of the real experiment and the counterfactual experiment will diverge. But at the same time, so it's one step look ahead type of problem. But at the same time, if we do that, we kind of learn the correlation between the real scalarizer and the counterfactual scalarizer. If they're similar, we can speculate that the physics behind this is also similar. If they're very different, then everything is very different. So there are other things that we can explore, and as I mentioned, this is very active exploration process when we can play with the kind of structure similarity, so trying to find out why the certain decision is being made. And as I mentioned, we can also explore the trajectories. So in this case, this is the counterfactual experiment when we have EI trajectory, when we have maximum uncertainty, when we have the UCB. You can see that the exploration is different. And I'll show you the example of the exploration for the yields dataset when the differences are much more obvious and clear. Finally, the question becomes, how can we learn what is that the DKL experiment actually exploring? So a real space trajectory is a real space trajectory. So when we look at it, we try to see whether the points are stuck in some particular part of the image, or they sample image space sufficiently broadly. But ultimately, we are interested in the small details. For example, we know that these exploration trajectories are different, but can we really say what are the different trajectories exploring? And what we can do in this case is basically use our favorite VAE approach and basically take all the image patches sampled during the automated experiment and represented as a feature. So using the latent representation of the patches sampled during the trajectory. So these are the examples of the latent space of the, latent representations for the different trajectories. You can see that they're different. So here the exploration includes the normal edges and this type of domains. Here you see the additional features that look like this one. So it is different. You may ask a question, isn't it the case that these are available only in the end of the automated experiment? Absolutely true. So these parameters, these feature spaces of individual trajectory are available only in the end of experiment, and they are specific for each trajectory. However, another thing that we can do is to remember that we have access to all the image patches from the very beginning. And therefore, whereas we can define the VIE analysis for each experimental trace, we can also define the feature space for the original image. And this is something that is available even before the experiment, before we start the automated experiment. So from the moment when we measured the overview image, we already have access to all the patches, and therefore we have access to the feature space of the image. And the feature space is basically the combination of the latent representation and latent distribution. So what you see here is basically the progression of the automated experiment, where we take the full image, calculate the VA embeddings, calculate the kernel density estimates, so it represents the density of the features in this space. And then for each trajectory, it becomes the progression in this feature space. So we basically see what interesting elements are uncovered during the automated experiment. Now, before we go to the notebooks, let me make kind of two general comments, which ended up being somewhat unconventional, and it kind of took a lot of time to understand that, even though in the hindsight it's absolutely simple. So currently we are using the microscopes like this. So we have human that issues the basic commands to the instrument, and the instrument generates imaging and structural data. Human analyzes this data and issues the next set of commands. So sometimes our basic command is take measurement on the grid. So this is a kind of universal approach by now. But nonetheless, the decision making is done by human. Once we start to have the machine learning agent, even the ones that I've shown here, the myopic Bayesian optimization type, the situation is now totally different. So in this point, we have a machine learning agent that issues the primitive commands and analyze the imaging and spectrum data. And the human basically overviews the operation of the machine learning agent. And the way that we can affect the machine learning agent is by these interventions: defining targets, defining the physics, defining the policies. In principle, the human can issue the direct commands to the microscope, but if absolutely necessary. But now let's look at numbers. So if we run the, so what's the difference between the human and ML agent running the microscope? For machines like classical AFMs or STMs, the human decision-making speed is roughly comparable to the rate at which microscope can acquire data. I mean, maybe within factor of 10. So human makes decisions within seconds. Most of our data would be something, spectral data would be something like 100 milliseconds. So in principle, humans are slower, but not that much slower. If we deal with the electron microscopes can acquire data quite fast, so at milliseconds, and they can acquire a lot of data. beyond what the human can visualize. Which basically means that for electron microscopy, we expect the machine learning agent being able to make hundreds and thousands of decisions at the time when the human will make just one. Which basically means that it's good to have an option for direct intervention, but ultimately we need to have some approach to ascertain the discovery path taken by the machine learning agent, and we need to intervene at the timescales much slower than the intrinsic timescales of the machine learning agent talking to the microscope. So this should be milliseconds. These can be seconds. But in this case, as I've shown you, the type of operations and type of tuning we are doing is actually very, very different from direct control. So after a while, the best analogy I was able to come up with is that once we start to have the machine learning running our instruments, it's no longer the case of switching from Toyota to Lamborghini. It's not even the case of switching from a bicycle to a Lamborghini, because bicycle have wheels, Lamborghini have wheels, they both have steering wheel, so we drive them roughly in the same direction. It's more like a case of switching from riding a horse to driving a car. So the principle how you control the system are totally different. So it's that different. Now, what is the future here? So the future is, of course, going to the full workflow optimization. So in this case, if we expand our definition of microscopy experiment, it's actually becoming a little bit more refined. So we need to start with tuning, imaging optimization, overview scan, optimizing spectroscopy, and then we can explore the statistically significant regions, explore outliers, and then drive the exploration driven by certain hypotheses. So throughout this process, we actually need to be able to go back to optimization of spectroscopy, optimization of imaging parameters. So this becomes a more complex workflows. This is actually the case where the reinforcement learning becomes relevant, and that's the reason why we explore it now. So that was a long lecture and introduced the large number of parameters. So for simplicity, I provided them as the table because we need to know what is global image, latent, scalarizer, acquisition, policy, trace, and the definition for the live, final, complete models, and so on. So there are a lot of new words, but let's see how it all going to look in the real world. So on the GitHub repository for these lectures, I have put two notebooks. The one which is called the GPAX 10 GPAX DKL Plasmon, and 12 the forensic one. So let's look first at the DKL Plasmon one. So this is the notebook that was made by Maxim about 2 years ago, and it has been optimized, actually not 2 years ago, maybe a year ago, and it has been optimized and improved several times, but it should be running. So I ran it this morning and it works. But let's look at the stages of the process step by step. So I'm not going to run, actually I can run it, it's actually pretty fast. So where it all starts is, of course, the installation of the GPAX as before. We're also going to use the Atom AI. So here we use it just as a utility function for the preparation of the input data. So as I mentioned before, once you work with the microscopy workflow, some of the functions reappear basically across all of the workflows, and therefore it makes sense to make it a separate function. So GPAX will take some time to install. Then we obviously install the relevant libraries. We'll give it a few minutes. So another important thing is that the great thing about the work that has been done in this collaboration is that it came with the early starter advantage in planning for these experiments and implementing them. Of course, that also means that a lot of things have been have had to be developed for the first time. So currently, it is considerably easier to repeat all this analysis. So you can use GPACs. Some of these things now can be repeated in the PyTorch. Not all of them, but at some level they may be. So anyway, going further, So we are going to install this. We are going to install the libraries. Then we are going to download our data set, which is basically the clean data set of the EELS data. Practically, it can be any structure property relationship data set, and this particular data set will represent the ground truth. So by definition, any notebook defined for the workflow design and optimization, you start with the pre-acquired data. Once you define it, you run it on the real microscope, then you generally don't have access to the pre-acquired data. So we can look at what the images are like. So this is our image is 62 by 75 points. Each spectrum has about 1500 points. We load the images, spectrum images, energy scale, and scale. We define our window size. So this is our patch size. And then we use the Atom AI in order to define our sampling grid and define our features and targets. So this is basically our ground truth. When we started from the spectral image, we converted it to the 2800 16 by 16 patches. So this is structure. And then we defined the equal amount of spectra, except that we average pooling them. So we need only 93 points. We don't need the full spectrum value. And then we also did the normalization. So this is the part where we essentially prepared our operation. And if you deploy the code on the real microscope, the only thing that you do is you define the window size. You don't have, you define the window size, and you also take the image, full global image, and you split it in the patches. So you will have access to this parameter, but not this parameter. So then the interesting part becomes we need to define the scalarizer. So scalarizer essentially says what type of physics I want to explore during this active experiment. And in this particular case, the scalarizer is defined as the maximum of the peak. So that's it. So our scalarizer is fixed peak position. So one of the experiments that you can run immediately is to experiment with the different form of scalarizers in this notebook. So we have spectrum kind of define whatever scalarizer you want. It can be fit by 2 peaks or 3 peaks, so you can use the LM fit for that. It can be area in some spectral band. It can be average from here to here divided by average from here to here. So that one is limited by your imagination. So caveat, of course, is that you are electron microscopist who is familiar with the plasmonic EELS, then you define the scalarizer based on your physical knowledge, because ultimately these peaks also have the physical meaning. But if your background is AFM or STM, just experiment. So then you create the scalarizer for all data sets. Again, once you create it and you plot the value, this is the plasmon peak intensity. This is the ground truth. So the important thing to understand is that the instrument does not have access to the ground truth. It has to discover it. Since we work with this workflow to just learn how it all works, we obviously have access to the ground truth. And then we can start playing with the deep kernel learning. So one thing we can do is to reconstruct from the partial data set. So see what we do here. So we define the split value. and we separate our data set and training and everything else. So in this case, we take this part of the image, we train our algorithm on this part of the image only, and then we try to predict the values of the scalarizer for the remainder of the image. So the first question is, do we even expect something like this to work? And the answer is, as long as the both part of the image are in distribution with respect to each other. So if we look at this part, we expect that here and here the distribution are the same. That's kind of roughly the same object. However, once it comes to the edge, we don't know, because here we have only edges between the particles on this size and this size. We have this hole, but on the unknown part, we also have the big edge. How does it work? We create model, initialize the DKL model, we train it. Notice that as everything that Maxim has built for the experimentalist, all the complexity is hidden under the hood. You don't need to worry about it, at least in the initial value. So our fitting function is only 3 lines. We do the fit, we do the prediction, see what happens. So now what we try to do is we use the features as we use the structural patches as features. We looked at the scalarizer values as the targets. We trained on this part of the image. We try to predict this part of the image. Again, the great thing about the DKL compared to the neural networks, normal neural networks, is that we have prediction and uncertainty. So see what happens. The prediction is actually very close to the ground truth. So this is our ground truth image. This is our prediction. They look almost the same. You can notice that they are not exactly the same. And it's actually kind of very funny that here, for whatever reason, the particles are oriented in the X and Y direction, so almost vertical. You see that once the boundaries between the particles are tilted, the prediction still kind of tries to be oriented along the X and Y. So it's a subtle effect, and to some extent, it's difficult to notice, but it does happen, and this is a kind of subtle example of the out of the distribution shift behavior. Second interesting thing that you notice is that there is the uncertainty, and uncertainty here, of course, is 0 or very small, because we sort of predict on the same data set that we trained on. But here the uncertainty becomes large, and notice the locations where it become large to the edge that has the orientation that did not encounter before. So here the edge is from dark to bright. Here the edge is from bright to dark. This one is more uncertain. And the uncertainty is large for the locations that look different than anything that was presented in the original image. So in some sense, that's expected, but that's a kind of good thing expected. It means that things actually work. So we can visualize the embedding space. So this is our latent variables. The fair statement here is that we did not explore the latent spaces for the DKL as in the same level of detail as for the VIE. So for the VIE, I've essentially spent 2 years exploring them in detail. For DKL, it seems that there are a lot of things that are common to with the VIE, but there may be differences, and it's something that is looking for exploration in some detail. Maybe not in a focused way, but something to monitor while you apply DKL for the real world problems. Now, another thing that we can do, and this is where it gets super interesting, is that let's try to do the reconstruction from partial data when we do the random sampling. So, and in this case, notice the important thing is that we sample from just 7% of the data. Why does it matter? It matters because the normal Gaussian process that treats the system as the black box will require something like 30 to 60% of the data to do a decent reconstruction in this case. The DKL requires only can work well below 10%. How much exactly? Sort of feel free to experiment. So in my experience, we were able to do the reconstruction for sometimes 3%, sometimes 2%. So 7 is kind of guaranteed, but see how it works. So this is our sampling. We've done the measurements only from these locations. This is our reconstruction. This is our location of the real image, and this is our reconstruction. So this is the ground truth. Actually, in this case, it didn't work, interestingly enough. Yeah, okay, so for 7%, for some reason, it's actually, this is, for whatever reason, the example when it didn't converge very well. So kind of experiment for it more, but it's a bit weird. As I said, in most cases, DKL reconstruction works well once you have about 5% of the data. And then the third thing that I wanted to show is the active learning. So in the active learning, we start with the seeds. So for the seeds here, I choose the about 0.2%, not 0.2, 0.2% as the train side. So these are my initial measurements. This is the so this is where we took initial values of the scalarizer. So this is the example of the DKL training loop. So we define some helpful function to plot the result. We define the number of exploration steps. And then you have the classical Bayesian optimization loop, which is you already seen many times. So we define the number of exploration steps. Then we take our model. We define our DKL model. We fit the model on the measured x values and y values. We calculate the acquisition function. We select the next point as the argmax of the acquisition function. Then we do the measurement. So in this case, we just take the value for the next patch. On the microscope, this would be the point where the algorithm sends the control command to the microscope. Then we plot the result, and then we update everything. We take our measured points and add the previously unmeasured point. We take the unmeasured point and remove the unmeasured point, and then we update our y's. Then we also update the indices. So look how the exploration process looks like. So this is our first measurements, and this is the acquisition function, which looks kind of very close to the ground truth in this case. Then on the next iteration, the acquisition functions start to look totally different because the process is kind of fluctuating. If we keep doing that, the acquisition function sort of changes up and down. And after several rounds of exploration, the acquisition functions start to look like the final image, meaning that our process is actually starting to converge. In the end, so we are now at the step 38. So once the experiment will be done, you will see that we were able to reconstruct. We are almost done, actually. We would be able to reconstruct our object actually pretty well. So, while it is going on, you can also see that we observe the same type of behaviors that I've illustrated during the presentation, meaning that sometimes in some location, the exploration happens in the distributed location, and sometimes the algorithm decides that these are the regions that I'm interested in. So let's see what happens. And another thing that notice that it is actually very fast, because this is actually a data set which is size which is reasonable. It's not unlike the real experimental scenarios. And you can see that DKL actually got trained for 80 steps while we are actually looking at it. So over the time scale of order of 10 minutes. which basically means that it is much faster than the classical Gaussian processes. I mean, of course, it becomes slower with time as all GPs, but again, there are ways to mitigate it in the real world scenarios. So let's see what it predicts. We are almost done. And this is our experimental trajectory. So this the color means the number of the points. So we started to explore here and here, and then we spent most of our time exploring the edges. Why? Because that was our scalarizer. And this is the overlay with the ground truth. And given our scalarizer, we basically discovered the regions where these behaviors are optimized. So the experiments that you can run with this is to play with the scalarizer function, play with the acquisition function parameters, so make it more exploratory, and obviously try it on your own data. So now, given that it's 11:40, let me briefly show you the notebook for the forensic analysis, and kind of maybe throughout for maybe 5 minutes. And after that, it would be great if you have any questions about the whole process so we can discuss it. However, this is the automated analysis also for stem mills. So you obviously have seen this picture. This is the part where we download the data and define the acquisition function. So this is a big production notebook, so it kind of requires careful going through it and the detail. But we define our functions, we download the standard Kevin dataset that we use for testing of quite a lot of ILS datasets. We define our patches and spectra. So this is where we define the window size. We create several scalarizers. So in this case, these are simple scalarizers simply based on the averaging within certain frequency band. You can see that since this is a nanoplasmonic data, the images, scalarizer images, look differently, meaning that they are sensitive to different aspects of the physics of this material. So, and then we can run the same thing. We can run the DKL on the full data set. This is how it creates our oracle. In the real experiment, the oracle is not available. However, in the dummy experiment, oracle is very convenient because it represents the full data that contains in our experimental data set. And also the oracle is oracle because what it gives does not depend on the experimental path. It is fixed. So we can see how it works on the same thing, original data set, predictive mean and variance. Notice that DKL actually can denoise the data rather effectively. It's a little bit inefficient to use the DKL for data denoising, but it's a beneficial side effect. Also, it gives us the uncertainty. Uncertainty is useful. So DKL uncertainty, even if it is trained on the full data set, essentially allows us to find the regions where something unusual may be going on. So it's a kind of convenient anomaly detection. We can play with the embedding spaces. We can play with the latents. So we can do the same thing for the 3 latent dimensions just to compare the results. So sort of feel free to explore that one. And then we simulate the automated experiments. So here we need to select the specific acquisition function, and we need to choose the scalarizer. So this will take quite a while to run that, but so that's kind of about half a day if you do it on the Colab. However, we can do that. We can get the answers for the direct and the counterfactual scalarizers. So the notebook should be sufficiently documented in order to follow what has been done. And then so you actually don't have to run all the experiments for half a day. There is a summary of the analysis. And then we do the forensic analysis, meaning that we visualize the behavior of the data. And this is how this is the type of information we have access to. So this is our learning curve, meaning how fast the total uncertainty of prediction decreases with the experiment. And total uncertainty of prediction basically means how well can you predict the scalarizer given the structural data. So the uncertainty of the prediction is basically the knowledge of the structure property relationship available in the end of the experiment. And here you can see how different would be the behavior for the acquisition function, such as expected improvement, the maximum uncertainty, and the upper confidence bound. So this is the complete model, meaning the full oracle. This is what is available for the end of this experiment. So this blue line is basically the model trained in this location. This is the learning curve that is available during the experiment. So see what happens. If we have the greedy functions, they have a very different learning profile compared to the pure curiosity-driven function. This one learns slower but steady, and ultimately gets to the kind of beta values. These ones learn differently. So the UCB learns faster, but then sort of stabilizes. This one learns kind of weird way. First it decreases linearly, then it jumps down. Also notice that there is as I said, the yellow curve, the complete model is always the same, but the blue curve have different widths. So width means the average prediction and the variation of prediction for all the possible patches. So you can see that this model has a very broad interval of prediction. And this happens because it learned when for some patches that it optimized for, and it learned poorly for other patches. So this one actually learned reasonably well for all patches because it was trying to minimize the overall uncertainty. So very different character. Oops, why did I go here? Okay, so these are the curves of the decal uncertainty for individual patch. So it kind of takes a little bit more time to go through those. These are examples of the ground truth value of the acquisition function. So it basically tells you how well can we optimize for the predicted behavior. So this is the same example, next point prediction. So you can see that this one actually minimizes our scalarizer. So we actually do optimization. And this one actually does not. So this one is purely exploration. It doesn't really care about the final value of scalarizer. We can do other things. For example, we can analyze the regret. This is a classical Bayesian term that essentially represents how does my learning rate compares to the ideally possible learning rate. So generally, the good algorithm has small regret. It kind of learns as fast as possible. Suboptimal algorithm will have high regret, so you can learn faster. And these are the models of how you implement the real world analysis for the different trajectories. You can see that EI, maximum uncertainty, or UCB trajectories are very different. So some of them spend more time on this individual particle. So this one explores it a little bit. This one explored it a lot. Some of them have different localization in the image space. So again, something that you can play with. And these are the implementation of the feature discovery for all trajectories. And this is the implementation of the exploration of the whole system in the image space, where we basically take all image patches, calculate the latent distribution, calculate the latent representations, and show the latent images, and ultimately show the experiment in the feature space of the original image. So in this case, I did not show the timestamp because I used the color in order to visualize the trajectories corresponding to the different acquisition functions. but you can already see that they are different. So if you see the localization of the blue dots, red dots, and orange dots, you see that they're sitting in the different part of the feature space, meaning that their discovery trajectories are different as well. So for a single one, you can visualize it using the color coding that shows you how actually the trajectory explores the latent space. So let me stop at this point, and I would be happy to take questions.
I actually have a question. So in the example of the, like you presented the ferroelectric domain and also the relation between it and also the, the loop area. We are not actually landing the, relation between the structure and also your loop area, right? We are landing the features calculated by the DKL with those area. Is that correct or?
So DKL learns to build the predictive relationship between the image patch and the loop area. So the DKL algorithm task is to learn this predictive relationship. I've noticed that it's a correlative predictive relationship in the fastest way possible. So there are several assumptions that we are making there. First of all, typically we talk about structure property relationship. Mm-hmm. Practically, we don't have access to the true structure. We have access to the image, right? Mm-hmm. We don't have access to the macroscopic polarization loop. We have access to the local polarization loop. So your question is very well posed in the sense that we learn the relationship between the parameters that are available during the experiment, and then we say that these parameters measured by microscopy are equivalent to their macroscopic analogs. Mm-hmm. So the great thing about the PFM is that this is actually very close to truth. It's a quantitative method. For other techniques, that may not necessarily be the case. For example, who knows what is the relationship between the optical reflectivity and the phase composition. But as long as there is any correlation, this approach will actually work. That's the strength of it. As long as you say that the changes in the phase composition are reflected in the change in optical reflectivity because of some mechanism that you don't quite understand, for example, the polishing damage or what's not, or micro roughness because of etching, this approach will work. That's a strength. You're also right in a sense that this clearly says the pathways to make it better, because rather than operating on the plane of observables, we can also throw the physical reconstruction in the loop. And if our physical reconstruction is sufficiently well defined, we can build the relationship between the known physical objects. Going into the more speculative area, you can also start to build the relationships that satisfy the physical laws in some sense. It's not clear how to do that at this point, so it's intuitively understandable that we need to somehow implement our known physics as a part of the reconstruction. We don't know how to do it yet, because to my knowledge, there is about 0 papers on the representation learning where somebody tried to add physics to that. And even for VAEs, for the DKL, it is more complicated because our latent space is updated each time we take a measurement. Mm-hmm. But intellectually, that should not be undoable. The difficult part here becomes when it will be useful, because one of the, say, limiting factor for me playing with the dummy workflows is that it already goes to the point that the number of points and variability in the dummy experiment is limited. And the reason I'm saying that is that if you have the pre-acquired spectral data set, it is rarely larger than 100 by 100 points, because otherwise you kind of have too much data. In the real microscope, you can easily operate on 1,000 by 1,000 spatial pixel. For electron microscope, you can operate on 32,000 by 32,000. So this is a kind of 6 order of magnitude more data that you can explore. And it's kind of a trap where currently we are limited to the data set that are convenient for human perception, meaning that they are too small for ML. So one of the next targets for work that we do with the Oak Ridge folks and the work that we do at UT is to deploy this algorithm on the real instruments and try to see how they behave in the real world scenarios. That probably will take some time because, again, we are going into the fairly unexplored regions of data acquisition, either for SPM or STM. So, but that's kind of what makes it interesting anyway.
I see. Following up a question is, I see that you are trying to find the points where you can maximize the loop area, right? Are there any physical meaning for that? And also if we want to build the the full relation between structure and also the loop area, for example, should we use the a exploratory acquisition function in this case?
So this is the point where probably the best way to proceed would be to take one of these notebooks adapted to the CITS dataset. So in principle, I have some notebooks when I did the GP exploration on the CITS from some data obtained by my Oak Ridge colleagues. If you want, you can take one of the data sets that you have at Jenny's group, and it may be much more interesting to basically just do it. It will take a considerable amount of time, but I expect that by the end of it, that would be pretty much a kind of publishable story, even though it is a dummy experiment, because you would be doing something that no one has done before. And secondly, you will develop a deeper intuition about how these things work on dummy data and how they may work on the real world experiment. And ultimately, it's much better to have this intuition developed actually before you deploy these tools on the instrument rather than after. Because when you run your concern is actually to make sure that the instrument works rather than tune the ML algorithm.
Yeah, that makes sense. Yeah.
Hi, Sergey. I just have a question with respect to the translatability of the ML methodology that you have used. In terms of, for example, if I were to do a DKL on PTO, for example, and then I study the hafnium oxide after that. So, is there any way that I could probably use the optimization of the hyperparameter space from one system to another? Would that be possible? And is there any reason to do that?
So the answer is generally, I don't know. So before we started, so the experiments that I've shown were done exactly the way that you propose. So it was done using the fixed policies that were tuned before the experiment. So the whole reason why we have the kind of this whole human in the loop workflow with the parameters that we can observe, meaning the indicator functions that we can monitor the process, and the parameters we can tune, is because we need to be able to tune the algorithm for the specific material, and we need to have the indicators that basically tell us how does the experiment proceed. So you work with Yongtao, right?
Yeah, I work with Rama and Yongtao.
So generally, currently we have multiple notebooks where this approach has been run for so band excitation, for EELs, for hysteresis loop area, for kind of pretty much all the scenarios for which we understand the physics and have the data. So I can suggest that the best strategy can be to kind of huddle with Rama, Yongtao, and myself, and figure out what may be the best strategy to convert the dummy notebooks into the notebooks that can be deployed in the real time. So this is not writing a single code. It's basically building the ecosystem, meaning that there is an instrument plane that you more or less have covered. There are the functions for analysis of the data on the fly that can be first developed as the simple functions and then can be developed consistently. So, for example, for a lot of folks in my group, the work for the next several months would be optimizing the function that then can be plugged and dropped on the real world workflows. And the good thing is that these functions are going to be the same for all scanning probes and all electron microscopies. There would be a difference in terms of the specific low-level analysis functions, like obviously how you analyze hysteresis slope is different from how you analyze the ill spectra, but the higher level abstractions, like how do you visualize the training process, how do you visualize the feature space, how do you visualize everything else, are exactly the same. So it makes sense to coordinate the workflow and the feature development. Obviously, the deployment at Oak Ridge and deployment at UTK would be very different, because in Oak Ridge you rely on the systems that have Stephen Bell controllers or nanoserves or Neon. At UTK, I will have the intrinsic Asylum controller and the autoscript from Thermo Fisher. So the instrument connections are different, but workflows are the same, and the principle of designing and building the workflows are the same. So there is no need to develop it separately.
Okay, thanks a lot. That's very interesting.
Hey, Sergey, maybe we could rephrase the question is, can you make a chat GPT for all scientific data? That would be really nice.
No, that's fundamentally possible, and that's not the right thing to do in any case, because ChatGPT, by definition, works on the data acquired before. Science is actually acquiring new data. And secondly, I actually had a LinkedIn post about it about half a year ago, when I said that the danger of the ChatGPT will be that it tends to reduce the things to the common denominator, meaning that if you have a very nuanced description of the system, send it through ChatGPT type model, and then use the outputs to train another ChatGPT type model, then eventually you will come to the level of the beige nonsense. So everything is the same. So maybe 2 months ago, there was actually the paper when people have done exactly that, and then came to conclusion that if you don't have the injection of new knowledge, then ChatGPT becomes stupid very, very fast. It's actually easy to prove even with the VAs. So if you take the data, some data set, train the VA, generate the outputs from the latent space, and then repeat the process many, many times, again, VA will become very stupid. So
it seems like a silly idea, but I guess who knows in the future? Maybe when you've developed a whole series of really good models for a whole different kinds of sets of data, you put them together and you've got different brains for different kinds of data. Anyway, I don't really expect that to happen, but I had a couple other questions for you, to be honest.
If I may, you ask actually a question which is really important. But
okay, good.
Notice what is going to happen. So in order to move anywhere, you have to do new experiments. So I know that we live in the world where it is believed that theory can do everything, especially because, relatively speaking, theory is now vastly over-invested compared to the experiment, especially on the ML side, to the point that very often the automated experiment activities are spun off from the theory groups rather than being developed in the experimental groups, much like whatever, 30 years ago, internet was developed by the people who worked on the CERN, exactly because they have a need to develop the computer technologies and they have the budget to do that. That being said, the problem with the theory is that it operates within the fairly closed world of the known laws. And of course, it does the important thing of formulating hypotheses and finding generalities, but the new knowledge comes essentially from experiment. So the new physical knowledge, mathematics is different, but new physical knowledge comes from the experiment, and the experiment is enabled by the development of the tools. Unless we develop tools and unless we run the experiment, the theory will become essentially a sophistry after a while. It will take a long time, but it will happen guaranteed, because the examples of the scientific system in ancient Egypt or whatever, or Greece or whatever, was that they ended up being closed loop. There was a limit to what type of knowledge they could generate. So new knowledge comes from physical experiment. Physical experiment are enabled by the instrumentation. Unless this is invested into, we are going to be stuck. Large language models can analyze the available, prior available knowledge, but not the new one. The places where they can become useful is actually this part, because the part where we say that define initial exploration targets in the experiment, this is the point where you have to rely on your own experience as the domain scientist. For relatively small images from specific material class, it's straightforward. That's why you do your homework before you stick the sample in the microscope. But this is the place where it is very easy to imagine the application of the ChatGPT, because even if I have a domain knowledge in ferroelectrics, I do not have the domain knowledge in other fields, which basically means that in this case, I can easily ask ChatGPT, what should I be looking at if I'm interested in the charge, if I'm looking at the charge density waves in the superconductive materials, and it can tell me that you should be looking for example, for the anti-phase boundaries or something like that. So on this stage, ChatGPT is actually useful. And another place where the ChatGPT-like models are useful is when you do the serendipitous discovery. They can really help you identify what it is and create this kind of, it's not the exploratory loop. The new knowledge is generated here, but this is the loop which allows you to use the prior knowledge in order to accelerate the discovery process and make it more meaningful. So there is a place for it in the scientific research, but this place is assistant, not the leader. Sounds good?
Sure, thanks. Yeah, no, that ended up being a more expansive but also useful answer than I had expected.
Okay.
For my potentially facetious comment, but it was good. Thank you. I was actually interested. I mean, it's a little bit outside of exactly what you were teaching in this course, but I was interested, based on my experience, the comments you made about how the field changed when Nion committed to supporting. Well, they built APIs, and then you were able to do a lot of the stuff you were doing. It made it easier. This is one of the biggest challenges for actually, connecting theory and experiment, or shall we say computational work and the experiment, is actually getting the instruments connected.
Yep.
So in many cases,
Absolutely.
you can't even do it. And I would sort of ask, just out of interest sake, does Nion actually commit to supporting the APIs into the future? Because that could be a limit. I have an example where in the lab I'm building, where we got some equipment and there were APIs, and the manufacturer was like, yeah, we've got these APIs. And then suddenly they said, well, yeah, we're not going to support them anymore into the future. We want you to buy this other thing that we don't have APIs for.
I mean, that's going to happen initially for quite some time. I mean, it does make it any easier in specific case, but there is a general progression that 15 years ago, when I talked to folks like Warren Oliver, in the MTI instruments. His point was, I want to sell the instruments at low cost, and I really want to get money by essentially selling the software upgrades every year. That didn't work out, because then Hyzotron came to existence, and basically people prefer to buy the relatively open instruments from Hyzotron than the closed loop instruments from MPI. So for the newer generation, I mean, I can easily remember discussions and the reaction if you suggest to the community of electron microscopies that the data and code should be open even 5 years ago. That was not received positively, shall we say. By now, the manufacturers actually start to be interested in the open code community, exactly because they understand the AI is a big thing and is going there to stay. And they also know that whereas as instrument manufacturers, they cannot provide the workflow solutions for all type of problems, what they need to do is to provide the sufficient flexibility and some form of risk management that allows the individual users to run those things. And it's very easy to detect it, because if you go for a dinner with the whatever Brooker, Oxford, or Thermo Fisher people, I remember how they were reacting 3 years ago, and I know how they're reacting now. There is a big difference. In fact, industry now seems to be actually getting to the point when they're more open to these ideas than the user community, which is good. There is a risk, because a lot of early development for the automated experiment for synthesis, I mean, how old is this field, right? The earliest comers, the earliest work that actually connected was maybe 2015, right? Less than 10 years ago. The tools that are made now are barely 1 to 3 years old, which basically means that manufacturers are going through a lot of fluctuations. Some of them say maybe this is the future. Some of them say that, you know what, we don't want to deal with the risk, because if the users start to implement the workflows and things are going to break, they're going to come back to us and say, where is the tech support? And all we can say is there is no tech support. We cannot support such different features. So, I mean, there's going to be very extensive fluctuations for the next several years, simply because there is push and pull between the user community that wants AI but doesn't know how. There are the early adopters inside the industry that typically struggle to create the business case for that. There are the product manager and the business people who ask what is going to be the cost model, how we are going to make the money with that. And for them, it is not obvious that addition of AI will generate the higher income, because on the one hand, yes, you can attract more users. That may be a good thing, but their markets are mature. People who use Thermo Fisher are going to keep using Thermo Fisher in the future. They have them locked, much like Apple. People who use Neon want to buy Neons. The market is small anyway. So for them, they don't feel that AI is going to disrupt the field. They feel that it can increase their standing in the market compared to their competitors, but it's not like you create an iPhone and you create a big new business. It's kind of changing the derivative. At this end, to the best of my knowledge, they're right, because that's kind of the type of things that Amazon taught me to do for a year. At the same time, they also know that if you add these features, they also come with the risks. You need to spend more money on the tech support and so on and so forth, which basically means that the VP for finance can easily push on the engineering people and say that maybe it's not the time for doing that. So,
yeah, I completely agree with your presentation of the business model and the associated problems. Like, these are things that I have certainly run into. And I would say it's, you know, just to, I know I don't want to have to extend the conversation a lot longer because I know people want to go, but I think this is a problem for material science in general for so many different pieces of equipment that I would love to have automated that just are not. And in some cases, there's no interest. And you may have to go out yourself and literally tell the manufacturer, if you're willing, I'll give you $50,000 if you will design this and build it just for me. And in some cases, you actually have to do that. And that's like the only way that you can imagine you will have the result you want. It's almost like a one-off, and somehow you have to convince them to do that because you're right, it's just not in their business model. They're,
then it becomes the case of the strengths as numbers. So first of all, most of the manufacturers don't necessarily care about the 50,000, right? Unless it is really small company like Ephemeral, right, or Thea or whatever.
Right.
Secondly, they start thinking about money if it is more than several mil. Second problem thing is that, I mean, there is always strengths in numbers, right? So if they feel that there is a customer interest, and so the request coming from one lab and one national lab is going to have a relatively small resonance. The request coming from the consortia formed by the several national labs and correspondingly representing a much larger customer base and also asking for much more mature concept and application.
To develop a relationship with them first, which is what you've done with some of these manufacturers, like the TEM people. They're partly interested maybe because they know you. But anyway, I'd be interested in the future, just for the kind of stuff you're doing, to ask the question, you've done so much for automation on the equipment, and one of your biggest stumbling blocks in the future to automate further could be, can you have the sample prep and sample loading automated? Right?
That actually can be done. If you look at how the electron microscopes on the semiconductor manufacturing lines work, that's actually that's done for semiconductors. If the sample preparation workflows are the same, then it's doable. Now here comes an interesting thing, another interesting thing associated with the how the automation is introduced. The thing is that of all the things that are done on the instrument, it by now turns out that the relatively quote-unquote low-tech one, like sample prep and sample insertion, are the ones that cannot be automated. So interestingly, if microscopy were not a R&D area, if it were more kind of manufacturing oriented, I could easily predict how the microscopy facilities would develop. They will have, instead of, let's say, 20 PhD level people for 10 microscopes, meaning that let's assume that you are running a user facility, your time on the instrument is 1/2 of your total time. If you have 10 instruments, you have 20 people running them, 20 PhDs running them. And then you'll have maybe, whatever, 5 technical staff making samples. So going forward, the effect of the automated experiment and machine learning for industry type of operation would be that you still have 10 instruments, you have 5 PhDs running them because they only oversee machine learning agent, and then you have something like 20 technical folks who make samples and load them. So it would be a very different balance between the high training level workforce and low training level workforce. And in fact, that's exactly how the organization such as the Emerald Cloud Lab operate. For the research organization, this is less likely to happen because ultimately the person running the instrument is also the one who is ideating what type of theory he or she explores. So I'm not terribly concerned, but there may be some interesting changes in the way science is going to be done in the 5 to 10 years. And again, there would be people who will be adopting it because it accelerates their business model. So there is a reason why automated labs are now everywhere in the bio and pharma. There are communities which will adopt it slower and only primarily adapt the developments in the adjacent communities. So as I mentioned, for example, for aforementioned automated experiment in microscopy, it is not, it looks like that it is not, it already basically the case that the automated workflows have not been developed by fundamental scientists and adopted by industry for fundamental scientists. They have been developed for the needs of the semiconductor industry, and they were flexible enough, then we can use them for our needs. So in some sense, you can argue that this is a little bit humbling experience, because we always think that fundamental science should be on the forefront of R&D, but it's not.
The intersection of fundamental science and sort of technique development that drives science, and like you're discussing, which is interesting.
I mean, again, that's the interesting part. Yes, and I agree that it's super interesting. And the important thing now, however, is that by now, so 3 years ago, situation was totally different. So 3 years ago, you need to, if you want to run the automated experiment on the microscope, you need to know how to hack the microscope through ActiveX. And I actually have seen setups where people basically make automated microscope by taking a stepper motor rubber band and connect this rubber band to the control knob on the instrument panel. So if it works, why not? So now situation is much better, because at least by now, most of the manufacturer give you an API, or at least talk about giving you API, and the process will accelerate, because if, for example, if Bruker comes with the fully functional API for their instruments, Oxford will follow almost by definition. So they may not want to be the first, but they definitely don't want to be second. So that's positive. For more complex chemistry synthesis workflow, situation is going to be much more complicated, because you have companies that want to make the case for providing the automated instrumentation. Generally speaking, everything that they are doing for the time being is very immature, because they simply didn't have the advantage of multiple R&D cycles to develop things. However, that's the nature of the beast. For example, on the aforementioned microscopy microanalysis, I saw the company that basically repurposed open-neutron pipetting robot for the sample preparation for the electron microscopy. It's like absolutely amazing idea. That's how the builder culture is supposed to work. I didn't ask for how much they sell it compared to the original Opentron, but you know, if people want to make money and there are customers, that's great. I do know that, however, that there is an interesting company called Theia Microscopy, which basically takes essentially a Raspberry Pi and provides a box with which as an input have the video signal from the microscope. As the output, it's the video signal which is segmented. Segmentation is done by the pre-trained model. So it's essentially the content of the box is sort of equivalent to the magic mirror that you can find on the Instructables. And the content of the box is about $500. Magic mirror is something that you can build at home with the minimal knowledge of deep learning, minimal knowledge of Linux, and minimal knowledge of IoT instrumentation, aka I have done it myself during COVID time, in about 3 or 4 days. So the selling cost of this product is about $50,000, and they have multiple sales by now. So that's actually amazing.
Indeed. Well, thank you for all your answers and your time.
So let's call it a day, but I would be definitely happy to continue. Also notice that generally the reason why we have this discussion is to potentially use it as a platform to launch the collaborations down the line, because that's where we are now. Good.
Thank you.
Okay. Bye.
Bye.